I want you to picture something for a second. You are walking past a massive, modern construction site right in the middle of a bustling city.
Oh yeah, machinery everywhere, the noise.
Exactly. You look up, and there is a skyscraper going up, floor by floor. You hear the machinery, you see the cranes, and you probably marvel at the sheer amount of concrete being poured into the sky. I mean, we all do.
Right. You look at the concrete and the steel rebar, and you just think about the permanence of it all.
But what we completely ignore, what is practically invisible to us, is the unsung hero that actually shapes every single inch of that building. And I'm talking about the formwork.
It is entirely invisible to the final observer, but it is arguably the most critical variable in modern high-rise construction.
Right.
Because without the formwork, the temporary molds that hold the wet concrete in place until it cures, that skyscraper is just a puddle of very expensive gray mud spreading across a city block.
Just a giant mess. And today, we are shining a massive spotlight on those temporary molds. Our source material for this deep dive is a really comprehensive guide from July 2026. It was published by Eleanor Industries, and it's titled Custom Aluminium Formwork Extrusions. Everything buyers need to know.
It is a great document, really gets into the weeds.
It really does. So our mission today is to look at why aluminum has quietly but completely overthrown traditional materials like wood and steel. We will look at how custom-engineered metal extrusions are genuinely helping to solve the global urban housing crisis and what it actually takes to manufacture these massive, incredibly precise metal molds. Okay, let's unpack this.
So it is a profound shift in the industry, but to really understand where we are now, you have to look back at how things used to be built.
The history of it.
Yeah. For decades in the mid-20th century, the construction industry relied almost exclusively on heavy timber frameworks and steel shuttering. That was the absolute gold standard for getting a building off the ground.
Like if you were building big, you were using thick wood or heavy steel panels.
Exactly.
But today, aluminum is the backbone of quality-conscious construction, both in India and globally. And I want to start with the physical reality of a construction site, because the primary driver for this material revolution basically comes down to physics. Aluminum is roughly 1/3 the density of steel.
Which fundamentally changes the entire operational tempo of a site. I mean, think about the human element here.
Okay.
When you have a formwork team handling aluminum components, they're moving these panels, beams, and prop systems by hand.
Just picking them up.
Right. They are repositioning them across multiple floors, passing them up through the structure, and they are doing all of this without constantly waiting for a crane to become available.
Because waiting for a crane is basically just waiting for money to burn.
Oh, absolutely.
I mean, think about the last time you had to move furniture. There is a huge difference between deadlifting a solid oak vintage dresser and, like, sliding a lightweight IKEA flat-pack box across the floor.
That is a perfect analogy.
And if you have to do that hundreds of times a day, the heavy material is going to slow your crew down to an absolute crawl.
It does. Crane time acts as a massive bottleneck on literally any site. So by moving panels by hand, you dramatically reduce physical strain on the workers, and you completely untether your schedule from the crane's availability.
Which speeds everything up.
Dramatically. On a high-rise or a fast-cycle construction project, this means formwork can be stripped from a cured floor and re-erected on a new floor every 3 to 4 days.
Wait, I have to push back here for a second.
Okay, go ahead.
Because anyone who has ever held an aluminum soda can knows that it is pretty easy to crush. You step on it, and it flattens instantly. So, sure, it is lighter, but isn't aluminum fundamentally softer than steel?
It is a softer metal in its pure form, yes.
So how is that not a terrible choice for a mold? If you are pouring thousands and thousands of pounds of wet, heavy concrete into an aluminum box, wouldn't the pressure just, blow the sides out?
It is a very intuitive question, but it kind of misses the magic of modern metallurgy and structural engineering, really. You aren't just using flat sheets of raw aluminum, you are using highly engineered shapes.
Like what kind of shapes?
Like beams with complex internal web configurations. The actual geometry of the extrusion distributes the load.
Okay, but a web is just a shape. If the material itself is fundamentally softer, won't thousands of pounds of wet concrete eventually just shear right through those internal webs? Like, how much pressure can a shape really hide?
Well, that is where the alloy chemistry comes in. You are not using soda can aluminum. You are using specialized structural alloys that have been heat treated.
Oh, I see.
Yeah, so when you combine an incredibly strong geometric shape with a hardened alloy, the strength-to-weight ratio just skyrockets. You get the rigidity required to hold back tons of outward pressure from wet concrete, but you do it without the crippling dead weight of steel. It handles the load perfectly.
Okay, so it is not just the material, it is the chemical recipe combined with the shape doing the heavy lifting. But even with that handling advantage, I mean, aluminum formwork is significantly more expensive upfront than timber. So if you are a developer, how do you justify writing that massive initial check?
You justify it by looking at the life cycle economics. Evaluating formwork based on its upfront purchase price is basically a rookie mistake that ruins budgets.
Right.
The correct metric, really the only metric that matters for a large developer looking at the balance sheet over time, is cost per use.
Let's break down why the traditional materials fail that cost per use test. Because our source material points out that timber formwork typically degrades after just 15 to 30 uses.
Which is nothing in commercial construction.
Right. And if you think about it, wood is porous. It absorbs the water out of the wet concrete, it swells, it dries out, it warps, and the edges chip from the crowbars being used to pry it off the wall.
And when the surface quality of that wooden mold degrades, it ruins the finish of the concrete it holds. You end up with bulging walls, wavy columns, and all these textured imperfections transferring directly into your permanent structure.
Which you have to fix later.
Exactly. Now, steel formwork lasts longer than timber, certainly, but
Yeah.
it introduces its own economic drain. It requires constant maintenance.
Because it rusts.
It rusts, it requires heavy anti-corrosion treatments, and under repeated heavy loading and stripping, steel is prone to dimensional distortion.
Meaning it bends.
Right. If a crane drops a steel panel too hard, it bends. It loses its shape, and a bent mold means a crooked wall.
Enter aluminum, which doesn't absorb water, so it never warps like wood, and doesn't rust the way steel does.
What's fascinating here is how the math plays out. Aluminum formwork panels and beams, if they are properly designed and maintained, routinely achieve over 1,000 reuse cycles.
1,000, compared to 15 or 30 for timber.
Exactly. So if you are a buyer evaluating a custom aluminum system that costs, say, 3 times as much as a timber system up front,
Yeah.
but it delivers 30 times the reuse cycles, it isn't just 3 times the value, it is 10 times the value. And that is strictly the material cost. We haven't even factored in the savings from dimensional consistency.
I was just going to bring up the dimensional tolerances because the numbers here in the guide are wild. Extruded aluminum sections have tolerances of 0.2 to 0.5 millimeters across the profile. We are talking fractions of a millimeter of variance on massive metal structural beams.
It is literally surgical precision on a construction site. When your formwork is that flat, that true, and that perfectly interchangeable, the concrete surface that cures inside of it is flawlessly smooth and perfectly plumb.
So, because the metal doesn't warp or bulge, you aren't paying a crew of 20 plasterers to come in later and chip away ugly concrete, or slather on thick layers of plaster just to make the walls look straight.
No, the remedial finishing work is virtually eliminated. The precision of the mold dictates the perfection of the cast. If the mold is perfect, the wall is perfect.
Makes total sense.
But to understand how they actually achieve a 0.2 millimeter tolerance on a heavy structural beam, we really have to look closely at the manufacturing process itself. We have to talk about extrusion.
Right. And for anyone trying to visualize the extrusion process, think back to when you were a kid playing with the Play-Doh Fun Factory. You know, you take a lump of Play-Doh, you shove it in the machine, you pick a little plastic die, maybe a star shape or a spaghetti string, you press down on the lever.
Yep.
The Play-Doh squishes out in that exact shape. Aluminum extrusion is basically that, but instead of neon dough, you are using a superheated billet of aluminum.
And a billet is essentially a massive, solid log of raw metal.
Right, a solid metal log. And instead of your arm pulling a lever, you are using literal tons of hydraulic pressure to force that log through a hole.
Yes. In industrial extrusion, that heated aluminum billet is forced under immense pressure through a highly engineered steel die. And that die determines everything: the wall thicknesses, the internal voids, the flange widths. But achieving that 0.2 millimeter precision is not just about squishing metal through a hole.
The engineering variables have to be insane to keep the metal from just tearing apart.
They are highly, highly controlled. The billet temperature, the extrusion speed, the temperature of the die itself, the quench rate.
Wait, quench rate?
That means how aggressively the metal is cooled with water or air as it exits the die. And then finally, the aging schedule.
What does the aging process actually do at a chemical level? Because it sounds like you are just leaving the metal in a room to get older.
It does sound like that, but it is actually a highly controlled heat treatment. Think of it like baking a chemical structure into place.
Okay.
When the aluminum is extruded, the alloying elements are mixed in, but they aren't locked down. Aging places the metal in an oven at specific temperatures to precipitate strengthening particles within the metal's crystalline structure.
Wow.
Yeah, it builds a rigid microscopic grid. It is what gives the finished profile its required temper and mechanical properties. If a supplier messes up the billet temperature or the aging time, the profile might look identical to a good one, but it won't have the structural integrity to hold back wet concrete.
It will just snap on site under pressure.
Exactly.
And our sources are very specific that you cannot just use any old aluminum recipe for this. The construction industry heavily relies on the 6000 series alloys for formwork.
Right, because the 6000 series, which primarily mixes aluminum with magnesium and silicon, provides the perfect triad of properties. You get moderate to high strength, excellent weldability, and fatigue resistance for repeated loading cycles over those 1,000 uses.
So they have this great base material, but they realized they needed to do different jobs on the site. For the heavy lifting, they tweaked the recipe to create 6061T6. This is the absolute workhorse of the industry.
6061T6 has a tensile strength of about 310 megapascals.
To put 310 megapascals in human terms, imagine hanging roughly 3 average-sized sedans from a single square inch of this metal without it snapping.
Which is incredible. It is remarkably strong, highly weldable, easily machinable, and widely available. It is the standard specification for most of your structural formwork beams and prop systems that are bearing the primary load.
But sometimes engineers want an even bigger safety net, which leads to 6082T6, which is often preferred in Europe.
6082T6 offers slightly higher strength than 6061. So for primary structural elements where engineers are pushing the limits of the design and want just a bit more design headroom and safety margin against failure, 6082 is a fantastic choice.
But then you have a completely different problem. When the metal actually touches the concrete, you don't just need strength, you need it to look like polished glass when you peel it away. So they invented 6063T6.
Right. 6063T6 has lower overall strength than the 6061, but it has one specific superpower, and that is flawless surface finish.
Why does a different alloy make the finish smoother? What is actually happening inside the die?
It really comes down to the friction during the extrusion process. Because 6063 has slightly lower amounts of alloying elements, the metal is slightly softer at extrusion temperatures.
Oh, I see.
So it flows through the steel die much more smoothly with less microscopic tearing or dragging on the surface. You use 6063P6 for the facing panels, the actual parts of the mold that physically touch the wet concrete. You use the exact right tool for the exact right job.
Okay, if these standard aluminum profiles, your basic generic I-beams and flat panels, are already this highly engineered, here's where it gets really interesting. Why go through the trouble, the long lead times, and the significant expense of ordering custom profiles?
Because modern architecture rarely relies on basic generic shapes anymore. Standard generic profiles work fine if you are building a simple conventional box structure. But if we connect this to the bigger picture, think about what is actually being built in modern cities.
Right.
You cannot efficiently build a curved wall, a sloped slab, or complex column arrangements with a generic flat panel system.
The geometry just doesn't work. You end up having to hack it together with plywood on site anyway to make the curves.
Exactly. Custom aluminum formwork extrusions allow developers to design the exact profile geometry required for the specific structural demands of that unique project. But it goes beyond just architectural shapes. Custom profiles allow for integrated system features.
What does an integrated feature mean in practice for the workers standing out in the rain trying to assemble this mold?
It means you build the solution directly into the metal itself.
How so?
Well, instead of having a worker manually bolt on dozens of separate loose clips, brackets, and bracing points on site, a custom extrusion can have tie rod channels, wedge clamp slots, and alignment pins engineered right into the cross-section of the beam.
So it's literally like a massive Lego set, perfectly designed for one specific building. Every piece just clicks into its intended slot.
It drastically reduces the number of separate, loose components required. That speeds up the on-site assembly dramatically, and just as importantly, it reduces the risk of human assembly errors. If the slot is built into the metal, you can't put the clamp in the wrong place.
And when you are doing high-volume repeat housing where a developer is building thousands of identical apartment units, using a standardized floor plan, the cost of creating that custom metal die is amortized over thousands of cycles. It basically pays for itself because you build the entire floor so much faster.
Yes. And that brings us to the role of aluminum formwork in the sustainable, rapid urban development.
Right. If you are listening to this and wondering how a metal mold is a sustainability issue, consider the alternative. When we talk about green building, we usually talk about solar panels or like the HVAC systems.
Yeah.
We don't usually talk about the molds.
But we should. Aluminum formwork generates essentially zero material waste on site. There are no degraded timber offcuts ending up in a landfill. And at the end of its life, after its 1,000+ uses, that aluminum is fully recyclable.
No.
In fact, melting down and recycling aluminum saves approximately 95% of the energy compared to producing primary aluminum from raw bauxite ore.
That is a massive verifiable benefit for green building frameworks. But the research also ties this directly to a very specific, very urgent human problem, and that's the urban housing deficit, particularly in rapidly growing places like India.
India is rapidly urbanizing, and the scale of the housing deficit is staggering. They need to deliver quality residential units at a scale and a speed that traditional timber construction methods simply cannot support.
You cannot solve a modern housing crisis if it takes you 2 weeks to frame and pour a single floor of an apartment building using wood.
You just can't. Custom aluminum formwork, specifically designed to standardize residential floor plans, allows structural floors to be completed in just 3 to 4 days per cycle. It isn't just about building cool architectural shapes. It is a critical tool for building safe, high-quality urban housing fast enough to actually meet human demand.
So what does this all mean for the procurement teams? With all these incredible benefits, speed, strength, perfect concrete finishes, 1,000 reuse cycles, a buyer or a developer listening to this might be tempted to just jump online and order the cheapest aluminum formwork they can find. How do they actually buy this stuff without getting burned?
Buying the cheapest extrusion you can find is a disastrous idea.
Right.
The guide provides a very clear survival strategy. The first rule, you must evaluate the supplier's actual manufacturing capability, not just their glossy marketing catalog. You have to ask if the supplier has in-house die design and management.
Why is in-house so critical? If they hire a great toolmaker down the street, why does it matter?
Because the die is the single most critical element of the production process. If a supplier outsources their die making to a third party, they lose direct, immediate control over the tooling that determines the tolerances of your formwork.
Oh, that makes sense.
If there is a flaw, they have to send it back out to be fixed, causing delays. You want a supplier who designs the dies in-house, manages their maintenance across the entire production run, and provides trial extrusions with measurement reports before you commit to full production.
So do not trust a baker who outsources their oven.
Exactly. The second critical factor is documented process qualification. For structural components that are going to hold tons of wet concrete over the heads of workers, a handshake promise is not enough. You need the mechanical test results. You need the dimensional inspection reports. You need material traceability, so you know exactly what foundry that aluminum billet came from. If a supplier cannot provide that documentation, you are buying on blind trust, and in high-rise construction, blind trust is dangerous.
I noticed the source material also dives into surface treatments, which seems like a small detail until you remember these molds are living outside in the dirt and rain. It says a mill finish, which is just raw, untreated aluminum straight out of the press, is fine if you're going to be spraying a release agent on it anyway.
Yes, but for high-wear parts, you want anodizing or hard anodizing.
What does that do?
Well, anodizing isn't just a coating. It is an electrochemical process that forces the surface of the aluminum to grow a highly controlled, incredibly tough layer of oxidized armor. It extends the life of the metal against constant impact. And for non-contact structural elements where corrosion from the site environment is the main concern, you might look at powder coating.
If you are a buyer trying to navigate this, the source material highlights Eleanor Aluminium, operating out of Gujarat, India, as an industry standard for this exact capability.
Eleanor is a prime example of an integrated operation. They have their extrusion plant in Gujarat, they do standard runs, but they also specialize in custom profile development. And crucially, they can produce matched hardware profiles.
What does matched hardware mean?
It means the connection hardware, so the pins and the clamps and the structural extrusions, are made from the exact same alloy and temper. They expand and contract at the same rate under temperature changes, ensuring everything fits and behaves consistently on the site.
That is so smart, and the research makes one final, really specific recommendation for buyers. You have to verify the supplier's track record, specifically in the construction sector.
This is vital. An aluminum extrusion supplier might make beautiful architectural window frames or highly precise consumer electronics components, but the construction environment is brutal. The extreme load cycling, the constant impact from hammers, the aggressive chemical cleaning to remove cured concrete, the wear and tear are on another level. You need to know that their quality system has been tested and verified by clients who actually build large-scale concrete structures, not just window screens.
All right, this has been an incredible journey. We started with heavy warping timber molds that were lucky to survive 30 uses, and we have unpacked how precision 6000 series aluminum is completely revolutionizing how we build. We've seen how custom integrated features and a 1000-use life cycle aren't just saving money on a balance sheet, they are literally reshaping cities and providing a viable high-speed solution to massive urban housing shortages in places like India.
This raises an important question, though, a philosophical shift, really, in how we view the built environment around us.
What do you mean?
Well, think about it. The next time you look at a towering concrete building, remember that the final permanent structure you are looking at is actually just the cast. It is the residue of a temporary mold. But based on what we've unpacked today, those temporary aluminum molds with their 0.2 millimeter tolerances, custom engineered profiles, and strict metallurgical controls are often more highly engineered, precise, and technologically advanced than the concrete they leave behind. Are we reaching a point where the temporary tools of construction are the true architectural marvels rather than the buildings themselves?
Wow. The mold is more advanced than the masterpiece it creates. That is going to stick with me every time I walk past a construction site now. Keep noticing the invisible systems around you, everyone. Thank you for joining us on this deep dive.